Okay, thanks for the introduction. Thanks so much for the invitation to be here for these next couple weeks. I'm excited. I changed what I was going to talk about, and hopefully I am talking now about something which is more exciting for many of you, although that also means that this is stuff that's still under process and I have never talked about before. So that makes you unlucky. But hopefully you can ask me lots of questions and we'll get through it together. I will spend, if I have time, the last 5 minutes telling you two teeny tiny stories about things I'm excited about, but I don't know if you will be excited about, and those are more complete stories. So I'll tell you that at the end. So this is the incomplete story, and that's what I'm going to tell you mostly about today. And so the framework, the question I'm sort of thinking about is, what is the sort of basic unit of deformation out of which I build an avalanche, and how do I figure out what that is in a disordered solid? And so I'll be using a model system where I have squishy disks that have no friction between them. It's sort of a standard model that people use in the jamming community. And I'm going to be trying to ask, what is the basic unit object structural defect that can generate avalanches or I can think about as being perhaps shear transformation zones, things like that. And so a lot of the work I'm going to be talking to you about today was done by my graduate student, Sven. I will also, if I have time, talk a little bit about some work with Andrea Liu, and then also maybe with some work with my really excellent postdoc, Max B. Okay? And so the motivation is that I'm interested in what leads to catastrophic failure in disordered solids, okay? And in particular, I'm going to be thinking about things which are composed like of a mat. It ends up usually looking like an interface, but I have, an idea of a structurally disordered solid made up of objects, be they atoms or particles or granular fault gouge, that sort of self-organizes to generate a localized region where a lot of the shear is accommodated, and eventually I'd like to understand how that happens. And so to start out, if I'm interested in what's the basic unit of deformation in a disordered solid, I sort of am going to ask the question, well, there's not really an idea of that in a liquid. If I have a liquid where all of the sort of molecules are disordered and I'm asked what a rearrangement is, they can basically happen anywhere. There's nothing sort of special about that place where it happened, okay? It just happens, and thermal fluctuations allow that to happen. But if I'm in a crystalline solid, then of course I know that rearrangements tend to happen at, for example, dislocation. So I'm sure you are familiar. I have sort of 2 lines of atoms here and only 1 here. So then if I shear the sucker, it's going to break right where the dislocation is and keep going, okay? So there's this inherent structural order that then gives rise to localized deformation. And so I would say the basic unit of deformation in a crystalline solid is a dislocation. It's pretty obvious what that object is. Okay, and so the question is disordered solids sort of look like this, but they have a mechanical response that's more like this. And so, you can even ask the question, is there a structural unit, or do rearrangements happen anywhere? So that's a question that I sort of started asking about 5 years ago. When I was a graduate student actually here in Santa Barbara, I worked on STZ theory, so shear transformation zone theory for deformation and amorphous sort of materials, and that sort of postulates that there do exist this pre-existing population of flow defects in the system, and then you write down a master equation for those and figure out what's going on. And it always sort of bothered me that I couldn't measure what that object was, that STZ was ahead of time. I could shear the material and then see it break, but I postulated that there was a whole population of these suckers, and figuring out where they were is sort of, or, what they are would be useful, because then you could actually fit the model parameters and it'd stop being a phenomenological theory and be a, something you could fit. Yeah.
I object to that presentation.
That's, since I worked with you, that you're allowed to object.
On the basis of work done by Manning, especially.
Uh-huh.
Okay. But the whole idea is that I thought, especially in that wonderful paper that you wrote on shear bands, was that these STZ defects were not pre-existing defects.
No.
That they might be more apt to appear at certain places If those certain places are themselves due to thermodynamic or noisy fluctuations.
You're completely right, Jim. So I think that
I'm only quoting you.
Let me make a distinction. Let me make a distinction. When you write down a master equation for STZs, you say that they exist before they flip, and then you have an equation that they come into existence due to things like thermal fluctuations or noise generated by avalanches. And so I think I'll get to your sort of question more at the end of the talk, but nevertheless, I think that there's this supposition that, at any given instant in time, that there is sort of a density of defects that exist, and then that changes as a function of time due to thermal fluctuations or noise. Is that a better characterization? Or driving, whatever you want.
There need not be
it's not a quenched, it's certainly not a quenched population of defects.
Not a quenched population of defects. And the time between when one of these things appears and disappears, or it makes it, may be not very much longer than the time for it to make a transition.
That's a great question, and one I'll try to address later.
Good.
Okay, I agree with everything you've said. I would still say that in writing down the master equation, you say that there is a population of these things even before you can see them flip. That's what you write down.
Yeah.
And then I agree that there's a question of, is the timescale over which they flip comparable to the timescale over which they form?
Yeah.
And I'll get to that question later.
You all get some sense of what it was like to work with Lisa as a graduate student. Or what she was like for
I was a pain in the butt. Well, it's a good thing I didn't know how famous you were when I started working with you, because I would have been much more quiet. Yeah, anyway, let's go ahead and move on. Okay, so the tool that I'm going to use to look at this is called the dynamical matrix. And so as you all know, the dynamical matrix describes the linear response of my material. And so that is if I have a displacement of every, say, particle or atom in my packing. And so this U is a vector of displacements of all the particles. And I multiply it by this matrix M, I can look at the sort of linear vibrational modes in my system. So this gives, M is a matrix that gives me the linear response. And if I have particles or atoms or something that interact via central force interactions given by some interaction potential V, then it turns out that the off-diagonal elements of this matrix can just be written as the second derivatives of that interaction potential with respect to the particle positions. No surprise there. Okay, and so for an ordered solid, the phonons are the eigenmodes of this dynamical matrix. Okay, and the eigenvalues give the phonon frequencies. Pretty straightforward. The good news is that for a crystal, there's so much symmetry that you can really write this in a very easy way. You use the fact that phonons have a wave number and everything collapses, and then this becomes a very small matrix. Okay, and you can parameterize it by the wave number k. Okay. So I'm going to be showing pictures like this a lot in my talk. This is what I'll call the potential energy along the mode. So this is, now I'm plotting it as a function of one dimension, and that one dimension is, I'm going to call a reaction coordinate along the mode. So this is, I'm displacing all the particles by the displacements that I got from one of these normal modes of this matrix, right? So this is, the potential energy is in n times d dimensional space, where n is the number of particles in my system and d is the number of dimensions. But I'm just going to be showing you along one mode. And the idea is that if I'm linearizing around a metastable state, which is what I do here, then I'm sitting here at this x. And then the curvature here is the eigenvalue, right, of my mode. And then if I push along that mode far enough, of course, nonlinearities happen. And then if I push far enough, I can push it into a new metastable state. And I don't have to push along modes, but I'm just saying if I did push along the mode, this is what would happen. Is that clear? Okay. So I'm interested in plasticity, not in the linear response, right? And so I just told you that if I'm interested in plasticity in an ordered solid, then I care about these dislocations. I have one dislocation, and those connect up into lines. And then if you're this guy, you can bend a spoon using your mind. because the spoon has all of these dislocations in it, right? Okay? And ordered solids, we know, flow via dislocations. And I'm not trying to trivialize this problem. This problem is very hard, the interactions between dislocations, but at least I know what the unit of deformation is in this crystalline solid, and I can describe flow. Okay? And I know that the nice thing about dislocations is they're really easy to find because there's an easy structural signature. Okay? But what I'm going to just tell you, which I didn't realize, but of course is sort of obvious once you think about it, is that the linear modes identify defects. Okay? And so to sort of illustrate this, I sort of love this paper. You basically can look at a stupid one-dimensional chain with two masses and then put a little spring defect in it. So these springs are different than all of the other springs in the system. So this is just a type of defect in a one-dimensional crystal. Okay? And then you can ask, okay, I can actually take this dynamical matrix for this one-dimensional problem, find the eigenvectors. So I'll be showing you plots like this where this is one eigenvector. So the blue line is along one mode and the red line is along another mode. Okay? And you can say, okay, I have all of these modes. What do these modes look like once I've diagonalized this matrix? And you see stuff that looks basically like a plane wave, no surprise. But you also see stuff that sort of has what people now call quasi-localized modes. So you see that there's a big displacement in the region where I have a spring defect, for example, right? And so you might be surprised that these show up because there's a lot of phonons at low frequencies, and you might think that they would hybridize and not show up at all, but that's not true. They do show up. And in fact, you can do some really nice analytic work, and you can say, as I change the spring constant for my defect, I can look at all of the eigenvalues in my system. And I see a lot of eigenvalues that don't change at all, right, when I change the spring constant. These are all phonons, basically. These are all the phonons in the system, acoustic eigenvectors. But then I have this localized mode that if it's above the acoustic band, it's truly localized at this defect. And then you can see that as I decrease the spring constant here, I'm basically driving this towards an instability by decreasing the spring constant. I basically drive it through all of these modes, and I can drive it to zero frequency. I think this is really cool because, of course, there's a no-crossing theorem for eigenvalues in these matrices, and you can see it's just narrowly avoided eigenvalue crossing. So what I'm trying to show you in this plot is, number one, you can find a defect in a crystal by looking for quasi-localized excitations. So the linear modes do tell you something about plasticity. The other thing that I'd like you to notice is that even though there's a no-crossing theorem, that there's clearly an idea of a defect, and I can see where it is, okay, in this system. Yeah?
But for a given spring constant on the left part, if I take a cut, how would I see this defect?
How do you see this defect? Well, that's what I'm going to be talking about for the rest of the talk today, except in disordered solids. But you basically look for a localized excitation in the sort of with a plane wave background. So let me show you an example in a packing. Okay?
Lisa,
yes.
Please explain the eigenvalue plot.
Yeah, sure. So this is, all I'm doing is taking, because you can actually do this all analytically, so you just take the dynamical matrix associated with this one-dimensional spring system, and all I'm going to do is plot the eigenvalues. So it's usually, this is what, you could see the density of states here if you sort of did this. The density of states is sort of this. And then I'm just saying, let me just show you what happens as I change the spring constant. So this is when this sort of perturbed, it's actually the ratio of this perturbed spring constant to the springs elsewhere. And if this spring constant is really small, then it turns out that this mode, there's a sort of a localized mode associated with this that's very sort of close to zero frequency. Okay. And that as I increase the spring constant, I can drive it through the acoustic modes. And then if I drive it all the way up here, it becomes localized again because it's not in a band of acoustic modes.
Okay. So this is for the linear spring?
This is for the linear spring, yeah.
So what are the modes that are crossing?
They are crossing because this is a two-basis system, so there's two masses. So it turns out that because this one is the small mass, it doesn't interact at all with the large masses, so that's why you see some crossing and some not.
In principle, each of these places where there's crossing, they would just touch each other.
Yeah. Yes.
In what sense are you addressing the problem that you're posing? You know, the reason you can identify this continuum mode is because you have a periodic system and then you have one localized mode.
Yes.
But you know that
So
it won't be the distinction.
Thank you. I planted you. I will come back to that question in just a moment. I agree. I agree. All this is showing you is that there's an argument in a crystal that plasticity can be seen from linear modes, which might have been surprising to you. It was surprising to me. And in fact, if I look at a packing with either a grain boundary defect, or this is a simulation with a couple of point defects that I put in by hand, what you can do is you can take the sum of, say, the lowest 30 vibrational modes in the system. So why you do that is because if you sum over a lot of plane waves that are pointed in different directions, it sort of washes the plane waves out. And so these colors in the back are how large sort of the polarization vectors are for the vibrational modes in that area. So let me say that one more time. The color scale in the back is basically what sort of happens if I sum the magnitudes of the polarization vectors on the lowest, say, 30 eigenmodes that I get from the dynamical matrix for the system. And actually, there is a way in colloidal systems, in 2D colloidal systems, to get the dynamical matrix directly from experimental data. So that's nice. And this is the same thing in a simulation. Of course, in a simulation, it's easier to do. And if you actually, so this happens to be a NEPA particle system, which means they can shrink it a little bit. And if you watch where rearrangements happen, or when you sort of shrink all of the particles, they sort of course, happen along this grain boundary. And that's what these white circles are showing you. There's also a few places where there's some defects in the bulk, and you can see that rearrangements happen there. So the point is that plasticity, of course in crystals, plasticity occurs where you expect it to, but you can also see it just by looking at the vibrational modes, okay? Okay, so the plan is to do the same thing in disordered solids, but as Leo points out, it's horrible, okay? That's the point. Okay, so let me sort of tell you why it's horrible. So the dynamical matrix is much bigger. It's n times d by n times d. Yes?
I guess even in the case of the crystal, so what you're saying is all these modes, right? Is something like so you're looking at you're not necessarily looking at the low frequency modes, right? They have to be localized.
Here I'm looking at all of the modes. It's a good question. So here I'm literally looking at all of the modes and summing them. The nice thing is that the localized ones add coherently, and the plane waves add incoherently, and so you still end up with a picture of the localized excitations if you just add them. I'm going to tell you in a minute how to try to do something a little better. Okay, so the numerical results I'll be showing you today are all this system. So it's a simulated frictionless 2D repulsive disks. And so they interact with either Hertzian or harmonic potential, which is either bubbles or elastic spheres in 3D, if they're touching, and they don't interact at all if they're not touching. They have a finite radius, but they don't have any friction. Okay? And so then the dynamical matrix is much larger. It's n times d by n times d. And in this system, really importantly, this is critical to understand, the dynamical matrix ignores changes to nearest neighbor contacts. So you can see in a system like this where the interaction goes to exactly 0 if they don't touch. If I were to shear this system, some particles are going to come in and out of contact, and the dynamical matrix doesn't really know about that. Okay? And so this is an important... It's a super nonlinear effect. Mark Robbins and I were talking because the Leonard-Jones system may or may not have this because everybody puts in a cutoff on their Leonard-Jones systems. But there's an interesting thing to ask, what is the same and what's different in a system that's a little smoother. Okay, so I don't know. It's not just
the cutoff, but the place where the cutoff is that matters.
Yes.
It's because if you have a cutoff that's sort of order of the size of the particle, you'll have rattlers and
Exactly. But interestingly, Mark Robbins sees a lot of the same things that I have been attributing to rattlers. So we can have a probably extended discussion about this. I actually think this is interesting. Okay. So, because they have, regardless of whether there's real rattlers or not, the potential is sort of short-ranged for Leonard-Jones. Okay, so all solids have a Debye regime in their density of states. So this is a density of states, which is just a histogram of the eigenvalues, that my vibrational eigenvalues that I told you about. And now we're looking as we basically decrease the pressure. So decreasing the pressure is this way. So what a lot of folks have seen and explained is that in these solids there's sort of this plateau that extends to lower and lower frequencies as you decrease the pressure. But the thing I want you to note is if I have a solid, it has a regime that goes like omega to the d minus 1, and it has to because of Goldstone's theorem. You can't get away from it, right? There's a cutoff where it stops acting like that, but it has to have that, except in the limit where it's exactly at zero pressure, okay? And so the question is then, if I have this Debye-like regime in my density of states, do those things look like phonons, okay? Because phonons is what I'd see in a crystal. And this is what some examples of what they look like in the Debye regime. So you see things which I would say look more or less like plane waves. Maybe this is a couple of plane waves mixed together. And you also see things that look like this, which is sort of a quasi-localized mode with a long-ranged quadrupolar tail of the sort we've heard about a lot already. Okay, and so they're not just plane waves. They're mixtures of plane waves. They have a lot of some of them have a lot of disorder. Some of them have less. Okay, so they're pretty messy.
So one
Yes.
question. In terms of the nature of these modes, how much of it depends on this particular to the system being in 3D?
Oh, that's a good question. That's a good. I'm trying to think. So Leo Silbert has a couple of papers where he's looked at some of these things in three-dimensional systems. And the claim is that, I mean, the claim is sort of that everything is the same in 3D. And clearly the quadrupolar tails are going to fall off differently, for example. I don't think anyone's carefully looked at, well, actually there's a recent paper with like Jörg Radler and a few other people that have looked at it. Anyway, I don't think there's anything in 3D for these quasi-localized excitations. The general features of the density of states look the same in 3D, and the boson peak modes look the same in 3D. So the what's the boson peak is the location of where this plateau sort of starts. That's called the boson peak in these systems. I might talk about that at the end if I have time. I'm sorry, that's not a good answer to your question. The answer is probably there's a lot wide open in 3D. Okay. So if I look at, again, so instead of summing over the lowest 30 modes, another really nice thing you can do is look at the Debye-Waller factor. And the Debye-Waller factor, again, just picks up the regions of the vibrational modes that have a lot of large polarization vectors. It's sort of the same thing. And so these color maps, again, are the Debye-Waller factor. And now this is for a supercooled fluid. And the black dots on top of it are the long time propensity, which is basically a measure of where the rearrangements are in the system.
So this is Leonard-Jones or something like that? It's Harrow, right?
Yeah, it's Harrow, so it's probably Leonard-Jones, but I don't remember.
Doesn't matter.
I don't know.
Oh, doesn't matter.
Okay.
But it's thermal.
It's thermalized, yes. It is thermal. And so this was sort of, I think, one of the first papers to really emphasize that basically, again, there's these localized hot spots in the vibrational spectrum, and that's where rearrangements occur. And so this is sort of suggestive, I think, that there are sort of structural places in the material that are structurally different, and that is where rearrangements occur. Okay, this is sort of an indication that that might be true.
But the structural places could change from
Yes.
one point to another.
Exactly, precisely right. So as the system evolves under temperature or under shear, these maps evolve. Okay.
remind me, the propensity is calculated at finite temperature.
Yes, it is.
Yeah.
Yeah, it's exactly. And actually they have this other measure that I like a little better, which is a metric for irreversible transformations in their supercooled liquid, and so that's a later paper. Yeah, they're basically the same thing. Okay. So the one thing that you can sort of ask right off the bat is, well, I sort of told you that this can't be true earlier. I sort of, but one thing you might think is, if there's a no crossing theorem for the eigenvalues, then perhaps all I have to do is look at the lowest energy mode in my system, and when that energy goes to zero frequency, because there's no crossing, you know, if I shear my system until that mode goes to zero frequency, then that's where the material is going to break, and I'm done, right? So the lowest, you know, the lowest energy mode should tell me where the material is going to break. So maybe I should just look at the very lowest energy one. And so that works. If you're close to where rearrangement is going to occur, close in time. So I'm straining my system, and I sort of get very close to where I know the rearrangement is going to occur, and then I go back just a teeny tiny bit and ask what's the lowest energy mode in my system. Then it looks like this, for example. So this is the whole mode, and this is just a zoom in of the localized excitation. And this is the actual displacements of the particles after a plastic event. And so this is the whole mode, and again, this is a zoom in of that mode. And yes, the rearrangement happens where the lowest frequency mode is. Yes.
So are you looking at, again, the divide?
No, this is actually the lowest frequency vibrational mode in the system. Okay. So I literally take the mode with the lowest omega, and I'm showing you what it looks like. Exactly. This is going to be below the lowest phonon. That's exactly right. So in the thermodynamic limit, the question is well, I mean, it's a question of limits, right? Because you take the thermodynamic limit, and I get more and more phonons. But it is true, actually, and catastrophe theory tells you that if I strain it close enough to the point of the rearrangement, you know, that rearrangement is going to have to go to exactly zero frequency. So in some sense, as long as you're willing to go close enough to the rearrangement, you should be able to see something that's quasi-local. It's a good question. You're right.
So then what does the color represent here?
The color represents the magnitude, and I'm just drawing the arrows to show you the direction. Just how big each arrow is. So this arrow's the biggest, okay, and that therefore it's red. It's sort of to help you guide the eye. Yeah.
So it's the magnitude of the displacement?
No, it's just literally the magnitude of that little vector.
But the vector,
What is the
vector is
The vector is the displacement of that particle along the mode. So I have a mode. The mode is normalized to unity. So the sum of all the polarization vectors squared has to, so all of this, the sum of these has to go to 1, right? But I can still have relative magnitudes between them. Yes?
Are you saying it's always the smallest mode?
Mm-hmm.
No.
Okay.
And that's where I think Itamar Prokacha and I, for example, disagree strongly.
I agree with that.
But anyway, yes?
So clearly, to find an instability, you have to find a zero mode, but then this zero mode can or cannot couple to the way you shear. Right?
That's a really, I am actually effectively ignoring that right now. And it's a good question. I will come back to it at the very end when I talk about how these might go into avalanches. What we find somewhat surprisingly is that if one of these things has a very low energy barrier, it seems to couple to sort of many degrees of freedom. It's very rare that you get a defect that only couples to shear in this direction but not in that direction. I'll come back to that. It's a good question. I'm ignoring that now. You're right.
And maybe it's related, but when you then observe the particles really to move, they move like this, or?
So I have chosen a special, very small event in my system, but I'm doing quasi-static shear. Mm-hmm. So some of the time it's a very small event like this, and sometimes it's an avalanche.
So it's bigger than
much bigger than that.
So this maybe is the beginning.
Exactly.
Okay.
That's precisely right. And I'll come back to, well, I might not come back to that, but yes, that's precisely right. Mm-hmm. It happens to be the entire event. Occasionally it's just the first part of the avalanche.
something which may be a little bit on the side, but at this point, we can talk about it later. Now, this is, in connection with the boson peak that you mentioned, based on the vibration density of states you showed in the previous transparency. So there, the characteristic frequency goes to 0 at the jamming point.
Yes.
Yeah. In the glass literature, the sort of understanding is that this is something that will go to 0 at the more coupling temperature coming from below. And I guess you're going to say this is something that's going to happen at some yield point when you're shearing the system. So these are all different things. And in particular, the first two are actually rather different because the way we might think about it, sort of these days, people think that the jamming point happens at a temperature, if you're talking about temperatures, below the glass transition temperature.
Okay.
Whereas the MCT temperature is above.
Right.
CT must be irrelevant.
So maybe
I'm raising the question.
let me just say something about the boson peak and the location of the boson peak and what it means for this talk, in my opinion. I'm going to tell you, if I have time at the very end of this talk, that I think that these localized defects or excitations that I find in the spectrum are actually tails of the boson peak modes. In other words, I think personally, based on some other stuff that I'm only going to talk about peripherally, that if I look at the density of states, I turned on the wrong one. The density of states, I just showed you a picture, has the Debye regime, and then it has the plateau, and then up here it has Anderson localization, right? Okay, and people say that somewhere around here is the boson peak, okay? There's lots of horrible definitions for it. Okay, and so the thing I think is going on is that the fact that you have disorder and global translation invariance tells you very generically that there is a group of boson peak modes that comes in at a characteristic frequency, omega star. Okay, and I'll call this thing the location of the boson peak in my mind. These are all random matrix theory stuff. It actually just has to do, I can tell you about it in detail, but okay. And so I think that it turns out that if you make a random matrix that has exactly these properties, they have a tail of completely localized modes here because they don't have any phonons. Okay? And I have a bunch of phonons in my real system because I have a system that exists in real space. So I have this band of, say, phonon-like modes here. And what I think is going on is that these localized, because you can ask in general, why do I expect to see localized excitations in low frequencies in disordered solids? They have to be here because there is a localized tail to this band of modes here that is truly localized if I don't have phonons. And then they're hybridizing with phonons. So I would say that actually once you use either your favorite, like Euclidean random matrices or your favorite random matrix, I think that localized defects are basically right at, come in right near omega star and below. So we can talk about that in more detail, but that's what I think is going on.
Why the lowest energy mode and not the higher energy ones? And are they also the modes with the longest wavelength?
The boson peak modes?
No. You're trying to look at the lowest energy mode and the correlation with particle rearrangement.
Mm-hmm.
So my question is, what happens to the higher energy modes? Do they tell you anything?
It turns out, there is the same localized excitations show up again and again in higher energy modes, but they're a little harder to detangle up at higher frequencies. Maybe I can talk to you in more detail about that after the talk. Okay, so this is a plot that you've sort of seen from other people before. This is the total, thanks, Sri. This is the total shear stress in my system, and I'm just straining it. And so you see the usual, there's some small events, small stress drops here, and large stress drops. And so there's some avalanches and some, not avalanches because I'm doing quasi-static shear. And what I'd like to do is look at the eigenvalues in a band between this stress drop and the next little stress drop. Do you see there's a little stress drop right there? And so now what I'm going to do is it's sort of the same plot I showed you before. These are all of the eigenvalues. Okay, so this is the lowest, say, how many? I plotted maybe 12, 15 eigenvalues. Okay, and this is now as a function of strain, and it's the same window of strain I'm showing you here. So when I have a plastic event, I have an eigenvalue go to 0 frequency. Okay, and then I sort of have some stuff, and then when I have another plastic event, I have an eigenvalue go to 0 frequency. Okay, so that's what I'm showing you. And then the colors are sort of the interesting thing, because what I did is I said, okay, I'm going to take the dot product of each one of these eigenvectors with the mode that goes unstable here. And that's what I'm showing you. So blue means I look exactly like this thing here, and the other colors mean I don't look like it at all. Okay, is that clear? So what's happening, what this plot is showing you basically, is that if I want to know about the mode that has this localized excitation in it, it started up basically up here. It's not the lowest mode at all. It was like, I don't know, the 8th lowest mode or something like that. And that's completely obvious once you realize that the no crossing theorem, doesn't really work, because simply because this tells you the same thing. I'm basically showing you a very similar plot here. This is what happens in a disordered solid. So the point that I'd like for you to understand from this plot is that I should look at some population of localized defects in my material, and I should look at some population of low frequency modes, because it's not always the lowest. It can come from much higher frequencies. That happens regularly.
But at the point of view, it is the lowest.
What?
By definition, it's the lowest.
At the end, it's the lowest. Yeah, it has to be, in fact. Right. But I think the point is that what you'd really like to do is understand what the defects are far away. Because so if I know it right before the plastic event occurs, who cares? That's easy. But if I really want to know what's the population of defects back here, and that's much harder. Yeah.
What are these small steps in between?
Oh, these are made in broken contacts in the system. So this is a granular system, and these square root singularities are made in broken contact. So you can see that happens a lot more often than a real plastic rearrangement.
And that has no broken contacts? That plastic rearrangement, or tons of broken
contacts?
contacts?
Tons of broken contacts, many more. Yeah, exactly. Many more. Okay. So about, actually, I guess 4 years ago now, I worked with Andrea Liu, and basically we wrote this paper on sort of doing the dumbest thing I could think of to try to isolate these defects in the system. And the first dumbest thing you can think of is, well, just filter the plane waves using a Fourier transform, and that doesn't work. I'll talk about why that doesn't work a little later. But what we decided to do is say, okay, if I'm trying to identify localized excitations in my system, and I think they should be inside the Debye regime, which basically means below omega star, or the boson peak on that plot over there, then I basically say, I postulate that there's a characteristic length scale for these localized excitations and a characteristic energy scale. They have to be below an energy scale, and they have to be below a certain length scale. And if I postulate that, then I can basically take all of these localized regions, excitations in my material, and group them together into clusters. Once I pick a length scale and an energy scale, then I can basically make a plot like this that shows all of the particles in my packing that have really large vibrational modes and also have energies that are below a characteristic energy scale. And then what I can do is I can optimize that choice, because I don't know a priori what that length scale or that energy scale should be, but I can say, okay, if I choose it right, then I should have the largest correlation with where rearrangements actually occur. That's what I do. So basically I say, I assume that there's a length scale and an energy scale, and then I go search for those. And the end result is that I get, and when I sort of optimize those two, I basically get a population of soft spots that do cluster together. There's nothing that says they had to cluster together a priori, but I do see localized excitations that cluster together like this. And if I ask, what fraction of the time when I shear the material does it break at one of these spots that I've identified, it's really, really high. Basically, you have to actually discuss how you're going to normalize a dot product here correctly between where the displacement occurs and where the soft spots occur, but it basically works really well. And we sort of go through all of that in this paper, that rearrangements happen at one of these soft spots that we've identified. Okay? Now, an open question is could I have a more minimal set of soft spots? Maybe. Yes?
and then when you have your event, then the other one which moves are the other soft spots, or?
So that's a great question, which I will come back to at the very end, but I don't have a full answer to that. The sort of short answer is, if I have
The question,
the question is, if I have an avalanche, do I break, this is the first one. This happens to be the first one in the avalanche. Do I break all of these other ones, or do I break new ones that form during the avalanche? I think. Is that a good paraphrase of your question? And so I would say that it's hard to know because of the following. I can ask what fraction of the avalanche broke soft spots, but it's hard to know how to normalize that dot product properly. What I can say, and I'll show you a plot at the end, what I can say is that because we identify a number of soft spots here, a typical number of soft spots, that basically if I look at the time between plastic rearrangement events and how long this takes to become decorrelated with itself, so if I take this map and ask how long it takes to become decorrelated with itself, it's completely consistent with avalanches breaking every one of these existing ones. But
those are athermal quasi-static avalanches.
Totally agree. And actually, the whole point of me giving this talk here is to say that actually I think this is a really interesting open question that I think I have an idea of how to answer, but we haven't answered it really yet. It's exactly the question I'm interested in as well. Okay. So all we've shown in this paper is that the first event correlates with one of these soft spots. That's what we worked on because it was easier to constrain. Okay, so this also happens to work in a 2D colloidal system as well. The bad things about it is that it doesn't identify, it only identifies the sort of spatial locations of these defects. It doesn't identify the directions of the displacements, where it have to move. And that means that I can't calculate, for example, energy barriers, which is something I'd really like to do because it shows up in STZ theory. It shows up in a lot of other theories for what's going on in these avalanches, right? And also, I get systematic errors at low packing fractions. And the reason that happens is because, of course, as you all know, as the system gets softer and softer as I approach the jamming transition, there's elastic tails on these. And the elastic tails, the quadrupolar elastic tails, start showing up more and more. You don't get the localized defects anymore because I'm looking at vibrational modes and the elastic tails show up there. Okay, so why do we have all these problems and how can we fix them? Well, it's because we can't really get completely rid of these background modes. We're still stuck with these background modes. And as I sort of mentioned before, if you try to filter them in some sensible way, like using a Fourier transform, it doesn't work at all. And that's because K is not a good quantum number for this system anymore. These aren't plane waves, really. Filtering them doesn't work. And these long-range elastic tails pollute things. Yeah.
Okay, but what you want to filter out are elastic modes, right? So that they would be good for your analysis.
So I've tried it, and I can tell you that the boson peak, these boson peak modes are sort of in the same area, and so you really tend to get extended disordered modes in there as well that are hybridizing, because these things don't, K is not a good quantum number anymore. So boson peak modes have similar frequencies to plane waves, and you really can't filter them out. I agree with you that sort of hypothetically you think you should be able to, because I sort of just told you that you're in the Debye regime. But so I can tell you what you can do is you can sort of Fourier transform them all, zero out everything below a certain wave number, and then move them back in, and you either don't get rid of all the plane waves and stuff in the background, like the boson peak modes that way, or if you make the wave number cutoff too high, you get rid of the defects.
So actually for the individual modes, you can ask to what extent they're plane wave.
Yes.
That's what we're discussing.
So that's easy to do. What I'm describing is if you then wanted to filter them, you could basically say, okay, I'm going to zero out the Fourier components up to, once I take the Fourier transform and figure out what the plane waves are that are there, I could basically try to subtract them off and then see what's left over. And what I'm telling you is when you do that procedure, you end up either having still background of some kind that's long range that's probably boson peak-like, or if you try to subtract off too much, you get rid of defects. I spent a long time on this about 4 years ago, and maybe somebody's more clever than me, but I wasn't able to do it that way. Yeah.
But I don't quite understand, what do you want to filter? I mean, it might even be that extended modes are important as nuclear avalanches or something, no?
Yes.
So you want to filter out those modes that somehow never go to zero even when you shear because they are phonal-like, no?
So I want to, given models like STZ theory and SGR and a few others, I would like to test the hypothesis that there is a localized structure, a very localized structural region that nucleates plastic deformation in the system. That doesn't mean it doesn't have long-range tails. That doesn't mean they're not coupled long-range elastically. But I really am sort of by construction looking for something which is localized. So you're precisely right. I am explicitly trying to throw away the quadrupolar tails, for example. Not because I don't think they're important for avalanche dynamics, but I just like to know where these, is there a basic unit for deformation? It might be the wrong approach, but that's what I'm trying to do.
The question is still this, how do you really connect these local soft modes with this long wavelengths plastic and elastic deformation? You have to go really to long wavelengths, right, to get that.
Yes.
So those are very short localized fluctuations. If
right.
you look at the lifetime, they're actually just flash in, flash out, probably within 10 to some picoseconds, right?
Right.
So how do we correlate that with something like these microseconds that what we see in the experiment?
Well, I would like to, because I would like to write down a model, if I can, like dislocation dynamics, because that's a very successful model. I would like to say I have these basic units of deformation that are coupled elastically to one another, or maybe interact with one another. And if I could write down master equations for their formation, interaction rules for their elasticity.
In order to do
right.
that, I think some people already asked this question before. How do you really connect this short lifetime soft mode with the long range deformation? Suppose I superimpose what you see with deformation method. Would they sort of coincide with each other?
Yes.
If they don't,
they
that's
do.
the problem.
But they do.
Okay.
They do. Yes.
But they don't always.
So if I have a very large avalanche that self-generates its own disorder.
That's the end of it.
Yeah.
So the interesting part is really you push toward this limit. When you reach the instability, suppose avalanche, one of the considerations for avalanche is instability. So by that time, there's nothing interesting. I mean, it's interesting, but not for what we are considering how to lead to that point. So that's where I think the connection here needs to be established, right?
So I'm getting impatient because the question, I think, was a confusion with people who are using the term avalanche. What I think they're meaning is these long-range sort of cascades of events that occur in quasi-static athermal approximations. But when I think of an avalanche, I think of a Manning-type shear band, like the ones that you showed in the very first slide, which have nothing to do with that.
Sure, but there's a large community here who are interested in the avalanches, and so I'm saying that.
I understand that all too well.
But so I think that these soft spots, I think that they are most useful in a system actually that's thermalized, and in a system where you're actually trying to talk about, say, for example, Jim brings it up, shear banding in a bulk metallic glass. I think there's a paper that just appeared in PNAS like this week by like Michael Falk and Ma at Johns Hopkins, showing that in a sort of like a realistic simulation of a bulk metallic glass, they've used this exact algorithm that I described to identify soft spots, and they show that both sort of local plastic deformation in that thermal system and sort of long time behavior are described by interactions between these things. So I can sort of show you the paper. I think the idea is that in a real thermalized sort of the best state-of-the-art model for a bulk metallic glass, you can generalize what I just showed you to those, and they do describe plastic deformation in that system.
another approach along this line with the same spirit is looking at the local, so-called local elastic constant.
Yes.
That's where your dynamic metrics can reach the long wave limit.
Yes.
Right? That's where this is relevant.
Right. So let me show you something because this might inform our discussion. And let's see. Let's see if I have this slide. I think I do somewhere. Here, I think. Okay. So one thing that I wanted to ask was precisely because it's been suggested that for example, a local measure of the local shear modulus is a good indication of where a defect is going to occur, right? Local shear modulus. Would that sort of be related to what you're talking about?
Right.
Okay. So what this is these black spots are the soft spots identified by the algorithm that I didn't really tell you about, but this algorithm, okay? And below it are sort of averaged over the typical size of a soft spot, the local coordination number. So that's a geometric quantity. And so what you see is that the soft spots sort of do tend to be lower in coordination number, but not always. So it's not one-to-one, okay? And then I can do bond orientational order. This is the interesting one. This is local shear modulus. So this is, at a given point in time, this is a map of the local shear modulus. And you can see if you just looked at local shear modulus and asked where it was lowest, you say, oh, this is the soft spot that's going to break. This is where my material is going to rearrange if I shear it. Okay? And what happens if you do actually continue to shear this material until it breaks at that soft spot. Okay? And there was actually not a very large hint of that soft spot in the shear modulus. Why is that? It's because the shear modulus changes extremely rapidly in these systems as you shear it. This local measure of shear modulus flashes. It goes extremely fast because once I change the force network in the system, it changes the local shear modulus very rapidly. Now, the structural properties that I'm telling you about that have to do with sort of regions which are really localized excitations are much more long-lived. They live a much longer time than these excitations in the shear modulus. And they're really structural things. And so that's why, but I think the interesting thing is that you really do need a population of them. Because if I just limited myself to the place that was soft and had a low local shear modulus, I would pick out this one and not this one. There's a population of them, and I think it's important to keep that for the whole time. Understand? Does that sort of help answer your question a little? For what it's worth. I really don't think this shear modulus is. I agree that right before the plastic event occurs, so this is the plastic event, right before the plastic event occurs, that one has to have the lowest shear modulus, by definition. But further away, it doesn't have to, and in fact, it really doesn't.
It's not a prediction.
It's not a predictor of where it's going to go. As long as you're if you're close enough if you cheat and go close enough to the plastic event, it tells you exactly where it's going to occur. If you're far enough away, it doesn't tell you anything. It actually, it's too sensitive. It picks out a local soft spot, but not the one that's actually going to go, because there's lots of them that are soft.
So is it related to the, when you showed us the eigenvalues, it was falling down very rapidly. Is it somewhat related to that?
I think so, but I don't have, I didn't look at that specifically. Jay, you look extremely confused.
Yeah.
I'm sorry.
It seems like, to me, I don't know anything about this stuff, okay?
Yeah.
But it seems like when you're trying to throw away the elastic tails, you're kind of throwing out the baby with the water. I don't know if that's an English expression.
Yes, it is.
Okay. Your soft spots are basically what you want. I think what you want to look at are linked soft spots, and the linking is by means of these elastic fields. So you're looking for if I was to think of this as a crack, which I guess I think of everything as cracks or whatever, but the biggest one is the nastiest one.
So I totally agree. I totally agree with you. But I think, let me tell you something, which is that I think the utility of these soft spots is good both, or possibly good. That's why I'm here actually, to try to decide if it's good. I think it's useful in the quasi-static regime where you get these elastically propagating connected objects. But I also think it's actually useful for things like thermalized bulk metallic glasses, where there's a lot more fluctuations and the elasticity connects things a lot less and you can be much more mean fielding. And so what I'm trying to do here, which maybe isn't what people here are interested in, that would be totally okay with me. But I think that what I'm trying to do is figure out because we saw a beautiful talk yesterday whereby the rubber band method, you were able to sort of tell us what's the critical nucleus that I have when I have one of these broken sort of fracture events, right, in a thin film. And so to me at least, it seemed that you made a distinction between sort of the first unit of the avalanche, right, and then the rest of the rest of an avalanche that would happen after that one broke, in a sense. And so to me, what I'm doing is I'm saying, okay, can I say an avalanche is going to be composed of elastically coupled soft spots, which are the objects which I should be, because if I can do something like figure out their density or figure out how they interact with one another, then I might be able to tell you about properties of your avalanche, like how big I expect it to be.
But that needs the coupling.
It needs the coupling, but the objects that I have to first tell you what is the objects that are coupled.
Yeah, okay, but then you want the guys that are, you differentiate between this cluster of black spots and this cluster of black spots, but the guys that are close to one another, you can take off your glasses and say, hey, that's one really big black spot or something.
Yeah.
And the taking off the glasses part, that's at least the near field elastic couple.
Yes. So I would say that if I have spots that are close together, then they're going to be strongly elastically coupled, right? And so if I was to write, and again, it might not be useful or interesting to people, but I would think that what you could do is write down a theory where you say, okay, I'm going to predict how big this avalanche is if I know where all of the defects are in the system that are, going to break, and then there happen to be elastically coupled, and I know they're coupling and I know how far apart they are. Well, then I could tell you, based on the energy barrier of this one, how big the avalanche is going to be long before the avalanche happens. And that's probably false, because probably what happens is the avalanche actually generates more soft spots as it goes dynamically. But I could also look at that and tell you, as a typical avalanche in this system goes, how many more defects does it generate? Where are they spatially correlated with it? Something like that. It's far from being done, but it's sort of an idea that, and certainly, that's why I'm telling you about the story. The reason I care a lot about this story is because I'm interested in materials that aren't as strongly elastically coupled, that aren't in quasi-static shear and aren't fracturing, but instead they're self-organizing into shear bands that occur over longer time scales. And in that case, I really think that the elastic tails are really not the important thing, and it's the structural coupling between them that's important.
You're talking about the biological systems.
No, I'm talking about bulk metallic glasses.
Okay.
So this is,
In that case, they are elastically strongly coupled.
They are strongly elastically coupled, yes. I'm lying.
Granular material is not.
Well, actually, that's not true either. There probably is no limit in which they're not strongly elastically coupled, really. But if some of the work I've done sort of suggests that if you're interested in shear banding, you might be able to neglect that coupling and still get a lot of the information out about how a shear band forms and how it widens.
That's actually a puzzle. If you look at all the things with a different coupling, they exhibit exactly the same microscopic phenomena. So that's the puzzling part, right? Either they're coupling or not.
Yeah.
So I guess I have two questions. How do you identify two soft spots are elastically coupled, and if you can identify them, are you actually saying that it gives you a hint as to where shear bands would form?
That's lots of questions. So the first answer is that the only way right now that I know that two soft spots are elastically coupled is if I quasi-statically shear and then they form an avalanche. I know they had to be elastically coupled because they break during a single sort of quasi-static time step, right? If I'm interested in trying to separate two soft spots that are very close to each other, the method I just showed you doesn't work. But the method that I'm not going to probably get a chance to show you in detail today does work, because I really do get localized modes that are really well separated from one another. And then even if they're close, I'm still okay.
Can't you just show us this other thing quickly?
Yeah, I'll just show you the other thing quickly. And maybe I'll come back to the last answer to your question at the end. this is sort of stupid, okay? But the idea is that I wanted to do something, because this is super inelegant. It's horrible. You identify a length scale and an energy scale, and then you do some stuff, and okay, it sort of works, but it's ugly, okay? So what I'm going to do is I'm going to say, actually, what I really just want is a high-pass filter. And the reason, basically, I want to really strongly penalize low-frequency extended modes, whether they be plane waves or boson peak modes. Just, I want something that penalizes things that are extended, to push them up to much higher frequencies. Because if I can push all of those extended modes to higher frequencies, then I'm left with localized modes all by themselves at low frequencies. And then I can just diagonalize things and find localized modes, and then I'm good to go. That's the idea.
I disagree with you. I don't think that's stupid.
Okay. That's what and actually, you know, it's not stupid because I got this idea while talking to Jim Sethna, so that's why it's not stupid, yeah.
So you would like something local that is soft, and you do not want that they linearly, elastically talk to each other, otherwise you throw them out, but later you want them to talk to each other non-linearly via elasticity.
I'm putting no constraints right now on whether they talk to one another, because what I'm trying to do is sort of get rid of all of their talking to each other just to find them, and then I'll go back and see how they talk to each other.
But if two things are at the linear level hybridizing,
yes,
then you would throw them out, no? Or do you have a method to sort of just say, okay, I break this into two parts and I keep them?
It turns out, I mean, I don't know, I can just show you data from numerics, but it turns out pretty generically that these localized excitations, once you push out the extended modes, have a sort of pretty good characteristic frequency, so they don't mix with one another too much. Because the phonons are what's coupling them, and they do tend to have unique frequencies. They're all low, but they have unique frequencies, and so if I push out the phonons, there's nothing to hybridize with because there's nothing in the density of states down there anymore. And so they just look like isolated things. Okay? So anyway, the idea is, and I'm going to go through this super quick because I don't actually think anybody's super interested in this, but what I did numerically is you put basically an artificial system of springs, and the objects that are connecting these springs are actually coarse-grained grid points that are basically the sum of the displacements of weighted sums of the displacements of the particles. So if I have a plane wave-like mode or a boson peak-like mode where the particles are sort of in some region going in the same direction, then this weighted sum over them is going to be large, right? And then if they're all going in different directions, then this weighted sum over them is going to be small. And then if I connect those sort of coarse-grained displacements by grid points, by square grid, for example, then I penalize motions like this and don't penalize motions like that. That's the idea. Okay? And the way that I'm going to sort of write that is that I have this new Hamiltonian, if you will, that's basically described by a new matrix, sort of, I'll call it an augmented matrix. These are the technical details. You write it like this. It's nasty looking, but easy. It's not, there's nothing funny here. And you can do it. You can just do this. That's all I'm doing. The important thing to note is that we use Gaussian weighting, and the reason we do that is because if you sum a bunch of Gaussians and they're close enough together, you get unity, which I didn't know, but sums of Gaussians are a partition of unity, and what that means is every particle in the end is equally weighted. So I haven't done anything funny to the energy of a single particle if I do it that clever way. Okay. Okay. So the first thing you can ask is we wanted something that's sort of a high-pass filter. And so what you can do is you can say if I put a plane wave in, sort of if I artificially put a true pure plane wave in my system, what's the extra energy that it costs due to this extra energy I put in my system? And you see curves that basically look like this. So this is a function of wave number in units of 1 over the Bach size, and this is the extra energy. And you can see that basically you get a high-pass filter. It's not quite so good when you get up to these higher ones because it goes lower again up here. But if you we use grid point equal to 5 for the data I'm showing you, and so basically you sort of get something that looks like a high pass filter with this thing. It costs a lot of energy if you're below the characteristic grid point spacing, and it doesn't cost energy if you're above it. Okay. And then I'm going to skip this plot. Okay, this is what happens when you do it. So before, when I looked at the lowest frequency eigenvectors in my system, I saw things that looked like this. The very lowest frequency eigenvectors in my system after I applied the augmentation look like this. So you have these truly sort of localized excitations, and they really don't have strong quadrupolar tails, which I agree is how they actually couple to one another, but what I'm trying to say is I think these are sort of basic little units of deformation in the system now. I've isolated them. Okay, I can also do the thing that people usually do where they sum the lowest 30 modes in the system, and this is what it looked like before I applied my augmentation, and this is what it looked like after. The thing I want you to notice is I didn't pick up I sort of didn't really change what it looks like, but I sort of clarified it. There's a bigger difference now between dark and light spaces in this because I got rid of some of the plane waves garbage in the background. Okay.
Is the correlation with light when it happens gets better as a result?
So that's the question I'm about to ask. Okay. The first thing I wanted to ask is, great, now all we have to do is show that these augmented modes have lower energy barriers than the other modes, than the dynamical matrix modes, and we're done. This is a quote from me about 3 months ago to my student. And so the idea is this: how do you look for? You should do other stuff too. You should shear it until it breaks and do lots of stuff. But the very first thing to do is just to say, okay, if I clean things up, then I sort of expect the energy barriers to be lower to rearrangements. And so you got to measure energy barriers. And so the way people in this field always measure energy barriers along a mode is you go along the mode and you wait until you get to a new state. Okay, so you say, oh, I'm in a new state down here, and then I look at the maximum potential energy just before I got to that new state. That's the energy barrier compared to where I started, and you can do that for any mode you want. So you can look at energy barriers as a function of modes. And this is done in the literature. So I told my student, okay, you have 2 days to do this, and then we're done with this part of it. And so this is the maximum as a function of the mode number. And what you sort of notice right away is that this is a little strange, because these are different packings that are supposed to be exactly the same, except just different instantiations. And you can see that there's a difference of like 2 orders of magnitude in their energy barriers between different packings, and then within a packing it sort of all follows the same trend. So it's a little strange when you think about it. And the way they define a new state, if you talk to them about it, is they say, okay, I'm in a new state as soon as I have a new contact network. Because these particles are touching, right? So they have one contact network, and then, you say, okay, because when contacts break, you say, okay, I'm in a new state when I have a new contact network.
Any new contact, like even one new contact?
Yes.
Or one change contact?
Yes.
That can happen.
Yes. So Booble has already discovered that there is, and I don't know why they did that, okay? Well, you can sort of understand, because actually Corey will say that that's the correct way to do it.
Yeah, but that would happen immediately.
Yes.
And you just don't think about the dynamic ranges.
Yes. Fine. Right. So, so Booble basically said, okay, if you have a different contact network, well, there are these things called rattlers that aren't touching anybody, and so if those join the network or leave the network, I should probably exclude those. Maybe I should say, okay, actually I need more than 2 particles changing neighbors to be a new contact. You could say, okay, I don't want it to move, it has to move far enough from where it started to be a new state. It has to have a bigger energy. This is similar to the question that Mark Robbins addressed on Monday. He used a cutoff on the kinetic energy. So he had a system with inertia. And so basically he said, I know that I'm starting an avalanche. I know I'm going to a new state when my kinetic energy increases above a threshold. But I just sort of want to point out, this is actually an open question, and these all give you different answers in these systems. So they all give you different answers. So this is the average energy barrier for the exact same packing, looking at lots of different modes. And these are the characteristic energy barriers in the system. And there's huge error bars on these, but the average is, reasonable. It tells you something. And so the point is that, of course, as Booble pointed out, any contact change, that happens all the time. So if that's a very low energy barrier. If I say I have to have too big of an energy difference, well, then I have too high of an energy barrier. The one that we think makes the most sense, and these two also agree with each other pretty well, it's pretty easy to see when you have a particle displacement that's sort of large enough to be a real rearrangement. It's also, you should have at least 2 contacts changing in like a T1 event, which is sort of the obvious object. So we're going to use this one as a cutoff, okay? But I think it's sort of interesting that actually there's these other things, and it's actually not as clear, okay? Okay, so that took a while. Okay, but now we're finally using these two, which both agree with each other and are sensible. Okay? And so then now I'm going to plot the barrier for the lowest energy barrier dynamical matrix mode. So this is the lowest energy barrier in my system as measured by a dynamical matrix. And then I'm going to plot the most similar augmented mode. Okay? And what you're seeing is almost all of them are above 0 on a log-log plot, which means that these more localized modes cost more energy. Okay?
The barriers are high.
The barriers are higher. Okay? So, this was not what I was hoping to see. I was hoping to see that these things, when I sort of got rid of the quadrupolar tails, they had lower energy barriers. And I thought that because if you think about like a Lifshitz criterion or something for when I'm going to get a rearrangement, if I have a really localized mode and I say, okay, I think I have a plastic rearrangement when one of my particles moves a significant fraction of its diameter, then if I just have a very localized mode where two things are going like this, and I push that should go unstable a lot earlier than, say, a long wavelength mode. Okay? So this is sort of, what happens? And then you realize, of course, and I think some people are nodding, they already knew this, and this is actually directly related to your question, right? Which is actually, any time I try to cut off the long wavelength behavior, I actually increase the energy. Okay? Not surprising. So if I have a sharp cutoff, which is a stupid thing, so what I'm showing you here is the same energy barrier divided by the energy barrier of the lowest dynamical matrix mode. And what I've done is I've just taken that same dynamical for these two things, I've just taken that same dynamical matrix mode, but I just artificially got rid of the long range tails. I just picked a localization length and looked what the energy barrier was for that mode. Okay? And so what you see is that, of course, for any mode, if I cut off the long-range tails, it actually costs more energy. So that's actually saying that these quadrupolar tails attached to a soft spot, if you will, actually lower the energy barrier by an order of magnitude. So I think this is somewhat interesting. And I think it's sort of related to the complaints that you all had, right, which is that, this unit of deformation, it is a unit. It's like, I think it's still, this sort of shows that it is sort of still like a dislocation, but the specific long-range tails that you attach to it actually make it more likely to avalanche in these quasi-static systems. It's easier for it to get started when it has the long-range tails. Okay. In the quasi-static system. Thank you, Jim. So I think this is basically, and I know I took up a lot of your time today, and I don't want to take up too much more. But so I haven't done anything with avalanches yet. The only thing I've done basically is say, okay, I can look at this soft spot distribution, and now this is a plot from the old way of finding soft spots, not the new way. But if I look at the soft spot distribution and I ask, as a function of the amount of strain that I put on the system, how much does this picture of soft spots look like the next picture of soft spots look like the next picture of all of the soft spots? In other words, how does this population evolve over time? And this is a quasi-static system, so it's avalanching all the time. And so what you basically see is that this is the characteristic average strain between rearrangements in a system of this size. So this is a finite size effect, but this is this for this system size. And you can ask, well, how long does it take for this thing to become completely decorrelated? And it turns out that it's basically, so this is 1, and this is a log-log plot, right? And so this says it takes about 10 times as long as the average strain between rearrangements for this soft spot population to become decorrelated. In other words, there's two things that are important about this. Number one is that the soft spot population is very robust. It actually changes incredibly slowly compared to other timescales in the problem. And the other thing to note from this is that it basically says, if I didn't tell you, but in this system size, the typical number of soft spots we find is about 10. Okay? And we find that sort of average over lots. So this is sort of consistent with the idea that basically I break all of the soft spots, basically, and then I get some new ones. Okay? It's not quite true, of course, right? Because I haven't tested that carefully. But it sort of says, okay, maybe a working hypothesis going forward, if I wanted to look at this, is that, if I have a system spanning avalanche, which happens in these quasi-static systems sometimes, I sort of break them all, and then I get some new ones. It's consistent with that. So that's a starting hypothesis. But one thing I could do, of course, is you can sort of calculate these soft spots during an avalanche and see what happens as the avalanche evolves. So that's something I could do.
I'll let you finish with the next question.
Yeah. That's sort of Okay, so I'm not going to say this stuff, but that's sort of the picture. I mean, I have 2 minutes, maybe I'll just say 2 minutes about the boson peak, if that's okay, in case it's interesting to people. I said 5 minutes, but whatever. Okay, so I already showed you this picture of, so this is a little different. So if you take this picture of the density of states, and then you divide it by omega to the d minus 1, then you get rid, of course, of the Debye scaling, and then there's a peak where it doesn't hold anymore. So this is also a way of finding the boson peak. And people would like to know what it is. And so I just want to tell you a cute little story because I think about vibrational modes, which is that this is a typical mode in the boson peak. It's sort of swirly and extended and disordered. I can plot a histogram of the magnitudes of all of these vectors. So each one of those vectors has a magnitude. Those little vectors has a magnitude, and I can plot a histogram of it. This is what the probability distribution, this red one, is what it looks like. This gray one happens to be a more plane wave-like mode. And then I can just take the cumulative distribution function. So I just am integrating to go from this picture to that picture. And then it turns out that all of the boson peak modes look nearly identical. There's a little bit of systematics I could tell you about, but basically they all look identical, which is kind of surprising if you look at pictures of these things, because they look totally, each individual boson peak mode looks totally different. But what I'm telling, because it's swirly and it has different features, but what I'm telling you is they all have the same statistics if you just look at the histogram. Okay, and so sort of the cool thing is that if you take a random matrix, and the random matrix has whatever you want for the mean and variance. You can pick it from a Gaussian distribution, whatever distribution you want. And then you say, well, if I'm trying to model something which is sort of solid, then it has to be globally translation invariant. And that means the dynamical matrix has to have the property that the sum of the on-diagonals is equal to the on-diagonal is the sum of the off-diagonals. Because that on-diagonal is the self-interaction term. Okay? So then you say, well, if I have n of those things, that are I'm interacting with, and I say, well, then the on-diagonal elements should have mean n times mu and n times sigma, and I'm going to make a whole class of random matrices, like whatever you want. Tried lots of stuff that has this property. It has exactly the same distribution. It is the distribution. So basically, I make a random matrix like this. And I look at the eigenvector statistics. So for the Gaussian orthogonal ensemble, this is called the Porter-Thomas distribution. I don't have an analytical expression for this. This is numerics. But the idea is that you basically just take the entries of your eigenvectors and you make a histogram of them. That's all this is.
So this is significantly different from Porter-Thomas?
Yes. I don't think I have that slide. It's not. It is significantly different from the Gaussian orthogonal ensemble.
Okay.
It's different.
Yes, of course, yes.
Yeah, so if you put in this constraint, it turns out.
The modes in that case are all extended.
So it turns out that they're right on the border. So there's a recent set of theorems on Gaussian Wigner matrices by Terry Tao and others that say that if you put anything in here that has compact support, so it doesn't scale with system size, then you're completely delocalized. You're still extended. But interestingly, as soon as you put this thing that scales with system size in there, then you sort of get modes in the middle that are extended. These are extended. And then you get modes in the tails that are localized. So it's right, it's sort of like, it's right on the edge. And actually I've talked to a couple of people, there's a couple of mathematicians now working on this. It seems like this is special. If you have n to the 1/2 or some other scaling, it's different. And this is really sort of the marginal case between localized and delocalized behavior. I don't know. That's what they tell me. This is no numerics. Yeah.
So what do you want simple people like me to think of when we think of modes in the boson peak? It looks as if you're getting some remarkable new intuition from the random matrix.
Yeah, I want you to think that boson peak modes are incredibly boring. Every material that has enough disorder and translational invariance will have boson peak modes.
And they're not fully extended, but they're spread all over the place.
So interestingly, and that's why I sort of drew this picture here with the tail, it's sort of a marginal case where the ones in the middle are basically indistinguishable from extended modes. They have what mathematicians would call delocalized. Nothing goes over 1 over the square. No entry goes above 1 over square root of n.
Are they sensitive to boundary conditions? Are they that delocalized?
Yes.
Those ones.
These ones in the middle are.
Those in the middle. Okay.
Yes.
In other words, if I
And the ones in the tail are not. And this is a marginal case. And so it's kind of, to me, it's kind of exciting for lots of reasons, but I sort of just wanted to, and this is a sort of a much more complete story that I'd be happy to tell people about in more detail. The other thing is that, of course, I made this, by calling this n, I made the assumption that these matrices were dense, because n is the system size, and in real systems, there is a coordination number that tells me how many things I have in contact. And so if you take that into account, it turns out that you can actually say something about the location of the boson peak in these random matrix models. And I don't have time to tell you about that.
So
but
the boson peak, in other words, if I take a box with a random matrix inside it, but I just change the boundary conditions so that I'm up on one side and down on the other side, or something like that for them.
I understand your question.
And then I can
that's
tell
an yes, that is a really, I haven't done that. That is a
the
very
kind of thing people did in the old days.
Right.
For localization. Yes.
The two of us are just old-fashioned.
No, this is good because I don't know this stuff, right?
Okay, but that's very interesting. In other words, if it's sensitive, you can see that you get a shift in that.
Yeah, this is something that Alan Middleton and I should just do together, actually.
Yeah.
Because he has the program to do it.
Then we really get a sense of what these things.
Yes, I think that's really, I think I haven't done nearly enough with this. There's a million things to do. And so that's a really good idea and something that Alan and I sort of talked about a little bit, but not really done. It's great. So it's an open thing. That's open. I would say that in the mathematician language, 1 over the square root of n is sort of, they say nothing is bigger than 1 over square root of n. It tells you whether it's delocalized or not, and these modes fit that criterion for delocalization, but I don't know about coupling, so that. Okay, so boson peak is boring and can be described by random matrix theory.
This is something that people have even said before, right? Looking at the Euclidean random matrices, the disorder and I don't. Yeah, we can talk about it, but I'm saying it's sort of been out in the
yes.
generic feature.
So you're precisely right. Euclidean random matrices have the same thing, but they're a very specific random matrix.
Yes, I understand.
I would say that this is the same idea, only saying that it's actually much more general than Euclidean random matrix. That's all. Okay, so this is really unrelated, but I just thought maybe it would pique some people's interest that it turns out that biological tissues actually have a critical scaling, a critical rigidity transition. So all this is for those of you who do like, some studies of I don't know, jamming, rigidity, anything. Maybe you've seen an Olson and Tidal plot like this where one side is a solid branch and one side is a liquid branch, and it's controlled by the density, right? You basically have a rigidity transition in granular materials or other things that are controlled by the density, and this shows biological tissues have the same thing, and it's controlled by this P naught, which is the ratio between a cell's perimeter and its area. And so this is totally cool, and I'd be happy to talk to people about that, but I just wanted to point it out in case anybody was interested. This is my postdoc Max worked on that, and he's great. Okay, so thank you. Yeah.
First, I agree, Max is great. So, so I have one.
Google's former student.
I have one comment and then a question.
Yeah.
So I think, and we can talk about this more. I talked a little bit about this mapping to the force styles, which you know about from Max's. I think there are geometrical signatures in there, which might get rid of a lot of this thresholding with soft spots, and we might be able to identify just through geometrical signatures what the soft spots are.
And Sam Schoenwaltz has worked on that with Andrea Liu recently as well.
With the force tiles?
Not with force tiles. Coming up with a geometric.
So I'm saying in the force tile picture, there are like qualitative distinctions between what you would call like where contacts break.
Yeah.
Let me put it that way. I don't know if they're soft spots or not, but that's where contacts break. But
yeah,
we can talk about that.
Yeah.
My then sort of more question is ultimately what you would like to do to understand plasticity, etc., is really to understand how these defects interact, right?
Yes.
And then my question is, identifying the soft spot, does that lead to sort of a program by which we could figure out what the interactions are?
I think so. So the idea would be as follows. In quasi-static, the way that you figure out how they interact is through avalanches, right? So the idea would basically be to say, okay, I'm going to watch an avalanche and I'm going to look at all the soft spots during an avalanche. So I'll use speed as descent or something sensible. And then I can actually just systematically look at how basically what's the, I would think of it in doing in terms of probabilities, what's the probability of this one flip, if this one breaks, what's the probability of this one breaking as a function of how far away, or not breaking, because see I have all of them, not just
so
one.
Can you do something more control? Like, is there a way of introducing these soft spots by hand in an otherwise no soft spot, and then ask what happens to them?
So
like,
this
that's
is
what
a
I would
beautiful
do
paper that was just published by Jörg Grottler and Jean-Louis Brott in PRE like a couple of weeks ago, where they actually put in by hand an STZ and watched the elastic propagation. They didn't pay much attention to the plastic but I'm sure that's on their to-do list. Now the question is a fake STZ similar or dissimilar to a real STZ? But you can't, there is a way of thinking about that, yes. So the other thing you could do, because now we know where these are and we know their displacements, you could also put in sort of what you think is a real STZ. Push along that mode and watch it couple as well. And then I would like to sort of, because Jim's here frowning at me, I'd like to say that also if you want to do it in a thermalized system, my guess would be, depending on the parameters of the strain rate and the temperature, that you might find, you would actually want to be more interested in how they self-organize over time. And that's something that you can easily get without the elastic coupling.
But if I really knew the interaction, I'd be able to say how they self-organize, right? If I really thought of these as the basic entity in a vacuum.
No, because I think that there's two ways in which they interact. I think there's the elastic coupling, which is what people here have been focused on. And I think also that when one breaks and dissipates energy, you get a local rearrangement of particles nearby, and that is what actually leads to new soft spots coming in and out of.
I would still argue that you can get both if you could do it properly.
I totally agree, but I would say that there's an elastic interaction and then there's a separate, longer time scale interaction between them.
Okay. So, can you identify where new soft spots would form following an avalanche?
That's something that we're going to look into doing. So no, we haven't done that yet, but we'd like to know.
So in terms of looking at finite temperature systems, in principle, nothing prevents you from looking at a sort of a vibration average free energy function rather than energy function.
Yes.
But has anybody done this?
So actually, this is exactly what Michael Falk just published in PNAS like this week, basically, with Mo. It got published this week, so I've only like skimmed the paper, but I'm pretty sure that's what they did. Yeah.
And my impression is that your work is focused on non-zero temperature systems, am I correct?
Well, this is zero temperature, but my goal is actually to think about non-zero temperature. Eventually, it's just that poses a lot more, you have to make more choices.
Also, can you apply this dynamical matrix approach to, say, purely repulsive contact, where you...
That's what you do.
But I thought that it was... Oh, okay, sorry.
No, but you can also apply it to attractive systems and basically even systems without even systems that have anisotropic interactions.
By purely repulsive, you mean repulsive, the finite range.
Yes, like contact interaction.
That's perfect.
We should let everyone go. If anybody wants to talk to me about this stuff later, I'm sorry I'm going to be so far over. Yeah, let's thank her again for a great talk.